Hello friends, and now we will discuss about the new topics, that is antenna gain, antenna directivity and efficiency. So what do you mean by antenna gain and how it is related to a directivity as well as efficiency? All these things we will discuss in this today class. Now, so what do you mean by directivity of an antenna? That is nothing but, for example, here we have taken an antenna at the middle. The antenna radiates power. So this is an antenna system and it radiates power. Here it is the maximum power it is concentrating, and here around this side the power is almost uniform. So now we can understand one thing. For example, this is the antenna system over here. The antenna radiates power like here or this. So this is the radiation pattern around all the 360 degree. For example, if it is so, what is happening? The directivity is nothing but, among all the direction of antenna radiations, only this particular directions the antenna concentrates maximum power. That is called as directivity. Clear? Right. So the antenna radiates maximum power in the particular directions. That is called as directivity of antenna. So the gain is maximum in the particular direction. That is called as directivity. So how we can formulate in this case for this with respect to some equations. So where directivity is equal to maximum radiation intensity to the average radiation intensity, that is Umax is this. Umax is over here, where U0 is the what is the average power transmitted around all other direction, that is called as U0. So same diagram is represented over here. So U0 is average radiation intensity, where UM is the maximum radiation intensity. So maximum radiation intensity occurs only at this particular directions, right? That is called as directivity. So now again we can write the directivity is equal to what is the maximum radiation intensity by the average radiation intensity formula is power radiated by 4 pi. So 4 pi is because it is the spherical coordinate component, so we have 4 pi solid angles. So again we can represent all these terms. We can write the equation can be written as 4 pi Umax by power radiated. So power radiated formula is written over here, that is Umax into sigma A. Sigma is nothing but solid angle or beam solid angle or beam area. So here Umax getting cancelled, we have 4 pi by sigma A. So the 4 pi by sigma A is the formula for calculating the directivity. So sigma A already we know, right? Sigma A formula is this. So this is the beam solid angle calculation, that is the area of total power, that is with respect to theta and with respect to pi, it has been calculated. In other way, the directivity can be calculated by taking the angular field component, that is theta E as well as theta H. So directivity can be calculated by taking 4 pi by theta E into theta H. So that is the beam width with respect to electric field, beam with respect to magnetic field components. That is with respect to theta and with respect to pi. Right. So now for the optimum value of the directivity for the dipole antenna is 1.5. So that is the maximum directivity of a current element is 1.5. It is the derived values. So here they have taken directivity is equal to 4 pi by theta into theta H, where theta is equal to pi by 2, where theta is equal to 2 pi. So while taking these calculations, and we are getting the answer is equal to 1.5. It is the maximum directivity of a dipole element, or that is infinitesimal dipole or a current element. Now we will discuss clearly about the relation between gain and directivity of the antenna. See here, this is the antenna systems. The antenna is fed with input power P in. Now the antenna radiates power is PRAD, that is power radiated, right? So input power is given to the antenna and power radiated is radiated from the terminals. So gain can be calculated by taking this input power. So for this input power, what is the intensity around 4 pi? That is gain is equal to 4 pi radiation intensity by what is the power provided to the antenna Pn. That is the calculation of gain. Whereas directivity is different, right? So by taking the directivity calculation, we have to take from how much power is radiated, right? from the radiated power of the antenna, what is the radiation intensity? That is 4 pi um by radiated power. So that is the small difference between your directivity and the gain of the antenna systems. Then the ratio between input power to this radiated power, that is given here, that is the factor K, that is radiated power to the input power is the efficiency formula. So K is the radiation efficiency, that is your K value will be equal to 1. If K is equal to 1 means the total power radiated is equal to total input power, that is without any loss in the wall of antennas. Whatever the power is provided to the antenna, if all the power is radiated, then you will get K is equal to 1. It means that 100% efficiency of the antenna. If K is equal to 1, your value of gain is equal to D, right? So your gain becomes directivity when if K is equal to 1. When K is equal to 1 is possible, if the entire input power is transmitted or entire input power is radiated by the antenna system, your K value will be equal to 1, that is 100% radiation. When it occurs, then we will get gain is equal to directivity of the antenna systems, right? So from this you can understand clearly about what is the relation between gain and directivity. So the gain is equal to K times the directivity, where K is the efficiency of the antenna, right? Efficiency of the antenna is nothing but how much power is radiated from the antenna for the given input power. That is the efficiency factors, right? Now these are the different formulas to measure directivity for different kind of antennas. For large antenna, this is the formula used, 32,400 by theta E into theta H. That is for large antenna directivity calculation. For small antenna directivity calculation, this is 41,253 by theta E into theta H. And with respect to effective aperture of antenna, the formula for directivity is equal to 4 pi effective aperture by lambda squared, whereas the relation between gain and directivity is equal to gain is equal to eta times the D, right? So eta we know already, right? What is the power input and what is the radiated power. So radiated power to the input power ratio, if we take, we will get what is the efficiency of the antenna transmissions. So gain formula is nothing but what is the radiation intensity by input power accepted by 4 pi. So 4 pi is nothing but it is the solid angle of spherical component systems. And see the picture, this animation shows about the directivity factor, right? So directivity is very high during if the power is converged towards the 0 degree. See here, if the beam is very sharpened, and you will get high directivity. The beam is widened, the directivity is less because the power is distributed around these areas, right? Almost this 180 degree the power is distributed earlier. So if the power is distributed from here to here in the wide area, where directivity factor will be very less. So now see here, now the high directivity, it seems that the power is concentrated only a particular point. The next animation, it shows about there are two different beams are located. The green color beam is the broad beam or wide beam, whereas the blue color beam is the narrow beam, right? So suppose if we want to transmit the signal or receive the information from this target, the green beam width or green radiation pattern will receive earlier than this blue, because blue is the very narrow. The blue color where concentrating power is very narrow, where beam width is very less when we compare with the green. So due to wide beam width of the green, it will easily detect the target. So target detection is located over in this graph, right? So that is the difference. So if the beam width is very narrow, the gain will be concentrated more. So that kind of antenna can be used for point-to-point communications or for tracking systems, where the beam width is very narrow, right? For wide beam width, it will be used for broadcasting the information. And this is the different antenna measurements we have. For example, here the gain measurements can be represented in terms of dBi. Why? Because always the antenna will be tested with isotropic sources. Isotropic antenna is nothing but the antenna which radiates power in all the directions, that is called as isotropic. Equal power in all the directions, that is called as isotropic. So the gain measurement always be done by isotropic sources. So the gain will be indicated with respect to dBi, and these are the corresponding gain measurements, right? For if it is 10 milliwatts, how to convert into dBm? The formula is given over here. So dBm is equal to 10 times logarithmic of what is the power we are getting by 1 milliwatts. So this is the formula to measure the power in terms of dBm, right? See here, 10 milliwatts converted into dBm is 10 dBm, whereas 100 milliwatts converted into dBm is 20 dBm, whereas 1000 milliwatts converted in the dB is 30 dBm. So what is the difference between this linear scale to logarithmic scale? That is, linear scale, it is completely expanded, right? So we cannot compress this data within a small scale or small graph. So the dB scale we can compress. So dB format is not only for compressed format. So we can make the compressed form of the whatever the input signal we are obtaining, right? And that is the graph it is located. So how we can plot the gain? So gain has been converted into dB. See here, 1 unit of power is 0 dB, 2 unit of power is 3 dB, and 4 is 6, 32 is equivalent to 15 dB, 1000 units is equivalent to 30 dB, and 31,622 is equivalent to 35 dB. So see here, the dB scales we can compress within 45 dB, but the variation is very less. Whereas the linear scale, it is varied from 1 to 31,000 something. So in order to compress the scale value, we are going for the dB scales. So how to plot in the graph? For example, if it is 20 dB gain, means we have to plot in the polar graph. Polar graph is the representing that angle versus gain. So we can, so this is the maximum gain. So we are going to locate 20 dBi over here. If it is logarithmic graph, it is frequency versus gain, and we can make this 20 dBi over here for the particular frequency. So this is the way we are going to represent the dB in polar graph as well as logarithmic graph. So all these things we have discussed about the gain and directivity relations, and how the directivity will be equivalent to the gain when at what level of k value. All these things we discussed. So with this we will complete the today class. Thank you.